Hi, this is day 14 of me coding every single day till I become a software engineer. And today we are on data structures and algorithms. I've already done the first 3 chapters, they weren't too bad, except for this last one I just did in sorting algorithms with the merge sort. I was really confused on the while loop. I forgot that while loops run as long as they are true. So if I wanted to stop, it needed to be false. So you need to use an and statement instead of a an or statement, which I was personally using. And also making sure that we added things that weren't added. So we went through both sides in the merge sort. I was originally adding everything that wasn't. It's just it's kind of hard to explain if you don't understand merge sort. But I was adding everything that wasn't in the first or second halves, and that was necessarily wrong. I need to add things that we hadn't gotten to yet, basically. So yeah, I had to ask Boots for quite a bit of help, but yeah, I don't know. I feel like it's better if I get some hints instead of sitting and staring at the screen for a long time, especially now with AI and things. I try to only use their AI thing because it only gives you hints and like does Socratic questioning instead of giving you the answer. So I feel like it's not taking away my entire thinking process. But yeah, there's something to be said about like if you don't know how to do something, you just kind of don't know how to do it. But yeah, definitely learned a thing or two here. Interesting way to do it, a lot cleaner than mine. Yeah, now we're on. It's talking about merge sort big O. What's a merge sort big O complexity? It's O of n log n, right? Yeah. I don't actually know why that is. I just know it from memory. Okay, so yeah, this would be n. We go through one time, right? The dividing part. We have 8 elements. It's split into 2 4s and 4 2s, then 8 1s. That's 3 different levels. Okay, so that's where the login comes from, the splitting parts, then the merging at the end. That makes sense. Okay. When might a merge would be a good idea? Need a fast sorting out of the memory is an issue because merge sort takes a lot of memory. Function is recursive. It's the merge sort function that's recursive. So insertion sort.
First, let me about when and why you would actually use insertion sort, and then I'll break down the algorithm step by step. Insertion sort is interesting because it's actually really slow in the average case, order n squared, but it has a niche use case where it's actually used in the real world because of how fast it is. And that's when the data is already mostly sorted and when the data set is very small. Some sorting libraries will actually use insertion sort when the data set is small enough and fall back to a different algorithm on larger sets. So how does it work? Well, it's actually one of the simpler algorithms. We start with an unsorted list of numbers. We'll iterate over each index or each position from left to right. And we're going to keep track of two indexes, I and j. I will be the index of the current number that we are on, and j will start at that same position, but it'll actually move to the left. I'll show you in a second. Now, because it's a look-back algorithm, we can actually skip the first index. We'll set I and j equal to position 1, or index 1, which is, of course, the second position. Now, the number doing the swapping will be the number at j, and the number at 1 less than j. I actually has nothing to do with the swapping. It's just kind of keeping our place in the algorithm. So we look at the number at position j, at the number at position j minus 1. And if they're out of order, we're going to swap them and decrement j. If they're already in order, then we can just move on and increment I. And whenever we increment I, we also move j back up to where I is. It seems really fast at first because I and j are close to the start of the list, so the amount of backtracking j has to do isn't very much. But you'll notice as I and j get larger and larger, we're gonna have to look back through more and more of the list. Now here's what a sped up version looks like on mostly sorted data. Here's what it would look like on completely random data. And here you can watch it be really slow on reverse sorted data.
Try something here. Just added some noise suppression and decreased how many decibels would go in. So hopefully I can talk without my family being so annoying. Guess we'll have to see how this works. Yeah, what's that? Sort big O all in square because the worst case complexity. Let's pre-sort doesn't have to go through the whole swap operation because it's already sorted. Yeah, X here half the time. X here every time. Squared. Probably O and right. Pretty fast. It's fast for very small data sets. So partially sorted. Not change the order of elements. All requires constant amount. Main production sorting was basically very small inputs. No recursion overhead, tiny memory footprint, stable sort. Yes, but only very small inputs. Rather than use the least memory and it's generally faster, respectively. Yes, insertion sort. Alright, merge sort is nope. So merge sort is actually faster. Interesting. Okay, quicksort.
Quicksort is fast and efficient, and unlike some of the other algorithms that we've covered on this channel, it's actually used in the real world. Looking at you, Bubblesort. Quicksort is a divide and conquer algorithm, just like merge sort. And while it technically has the same big O complexity as merge sort, order n log n, it doesn't require so much memory, and it doesn't have to copy elements from sublist to sublist. It actually sorts the entire list in place, which means that it can be more performant. All right, let's dive into how it works. We'll start with a random list of numbers. The first thing we need for quicksort is a pivot number, and to keep things simple, we'll just arbitrarily use the element at the end of the list. In this case, 5. Next, we need 2 pointers, I and j, to keep track of things as we're going to be swapping them around. I will start at index -1. Which of course isn't a real index, but we need to be able to increment into index 0 on the first swap. Then j will start at index 0, which is 8. So in this case, we'll be comparing 8 and 5. And because 8 is not less than 5, meaning j is not less than the pivot, we don't move I, but we do increment j. Now we do it again. We compare j to the pivot, 3 to 5. And because this time j is less than the pivot, we increment I, then we swap I and j. Now I understand that it's a bit funky. We are comparing j and the pivot, but actually swapping I and j. Just remember that. All right, and now we just do it again. So now we'll compare j to the pivot again, in this case 2 and 5. And again, because j is less than the pivot, we increment I, and then we swap I and j. Next, we compare 9 and 5. Now this time j is greater than the pivot, so no swaps. We move j forward, but we do not move I forward. 1 is less than 5, so we move I up, and we swap I and j. 7 is greater than 5, so no swaps here. 6 is also greater than 5, again, no swaps. 10 is greater than 5, no swap. 4 is less than 5, one last swap. All of the numbers at or to the left of I are smaller than the pivot, and all of the numbers to the right of I are greater than the pivot. If we swap I plus 1 with the pivot now, then the pivot will be in its perfectly sorted place. Now, that's just one round of the partition function in Quicksort, but frankly, it's the interesting part. The way we turn this partition function into a full-blown Quicksort is by recursively calling this partition function, so we'll continuously partition, do this algorithm, over and over on each half of the list until the full list is sorted. Now, remember how I mentioned that Quicksort is generally more performant than merge sort? That's true, but it does have a dark side. If we consistently pick the smallest or largest element from the list as the pivot, it gets really slow and will actually degenerate into order n squared in big O terms, which effectively makes it a bubble sort equivalent, which is something that no sorting algorithm wants to be. But honestly, that shouldn't scare you. There's pretty trivial ways to make sure that Quicksort never degrades. For example, we can just check and make sure that the list isn't pre-sorted. We could randomize the list before sorting it, or we could even pick the pivot random for maximum chaos. Anyways, optimized versions of Quicksort are used all over the place in the real world. Most languages' standard libraries actually do use Quicksort, at least for part of the standard implementation of their sorting algorithms. Now, so you can properly visualize it end to end, here's a full animation of Quicksort on a larger dataset. And here's another full animation, but where the list is already sorted and the performance degrades. You'll notice that it's a lot slower.
Interesting, it's slightly confusing, however it makes a little bit of sense. It's like a pivot element. Arbitrarily choose the last element in the list. Move through all the elements of the list and swap it around so all the numbers listed in the pivot on the left is greater than the pivot right. Move the pivot between two sections where it belongs. Push repeat both sections. Do sorting algorithms, dropbox, and backend. Quicksort and project function. Set pivot to the elements at index high. Now it's according to high. So high to index below low. So high is equal to low minus 1. Or each index j range of low to high. If the element j is less than the pivot element, then increment I of 1. Swap the element index I with the element at index j. A temp is equal to j. Set j equal to I. Temp is equal to num scoring to j. Num scoring to j is equal to num scoring to I. Set num scoring to I equal to the temporary. Swap the element to the right of I with the pivot element to the right of I. So nums plus 1. Nums I plus 1 equal to the pivot. Set pivot equal to temporary. Return the index of the new pivot element. Item, okay. Return the index. How to get index of an element in a list, right? Python. Pretty sure it's a list. Yes, index. Turn nums dot index of pivot. Now with quicksort, if low is less than high, partition the input list using the partition function. Partition Numbs. Partition. Store return middle underscore index. Carefully couple Quicksort on the left side, so that would be up to the middle index. Wait, nums up to the middle index. Zero, I think the length of this, -1. That's what it's supposed to be. We're gonna do the same thing for when we start the middle index up to the end. Because we need this other Quicksort to start from 0, right? First element of this split list up to the last element of that split list. Okay, I guess that's it. Saying 6 is not in the list. Oh, we're not supposed to be removing stuff. I is equal to temp, right? Not exactly sure why this is happening. Here's input list. Just restore the returned middle index.
They're gonna cut down the old oak tree at the crossroads. Why?
Kind of confused here. I don't know why. Why is the first one even failing? It's like it's not returning. I don't know that anything is changing here. And pivot. It.
Quicksort is fast and efficient and list in place, which means I and J keep track of things as we're going to be swapping them around. I will start at index -1, which of course isn't a real index, but we need to be able to increment into index 0 on the first swap. And then J will start at index 0, which is 8. So in this case, we'll be comparing 8 and 5. And because 8 is not less than 5, meaning J is not less than pivot, we don't move I, but we do increment J. Now we do it again. We compare J. To the pivot, 3 to 5. And because this time J is less than the pivot, we increment I, then we swap I and J.
I don't know how I'm comparing the index J to the actual element J. Okay, now we're getting a different error. Okay, we probably got a dumb mistake around here. Relative to the element index.
Okay, now I understand that it's a bit funky. We are comparing J and the pivot, but actually swapping I and J. Just remember that. All right, and now we just do it again. So now we'll compare J to the pivot again, in this case 2 and 5. And again, because J is less than the pivot, we increment I, and then we swap I and J. Next, we compare 9 and 5. Now this time J is greater than the pivot, so no swaps.
J is never greater than the pivot. So it's just swapping 2 and 2, and that's not doing anything. They're all staying in the same spot. Okay, first of all, the second supposedly moved the pivot. It's not moving the pivot at all. It's in the same place. Something's wrong. don't know exactly what's going on here. That's J, I plus 1 is the pivot. 1 for the pivot, I plus 1. We set temp. P1. Set P to be 2. Now it goes 2. Then we set I plus 1 to be 1, which is also 10. Oh, must be I plus 1, right? No, it's not. Yeah, we're just resetting. It's not what it's supposed to be. I draw here. Give it a 1. That tends to be equal to 2. No, it did swap correctly. Damn it, no. I mean, no, yeah, that's right. Alright, it's already 11 o'clock, I'm tired as hell. I'm not exactly sure what's going on here. So by passing new arrays, we're changing the indexes. I guess that's what this was about. I want to be a same array, but I want to work on different sections. Maybe the left half is 0 up to the middle index. Then the right half is the middle index up to the end of the list. Maybe not. I'm not sure what's going on here.
Intruder! Get over here! You should be glad you're still alive, you piece of shit. Now bugger off and don't come back. Well,
Okay, I'm gonna stop the video here. I'm tired. And look at this tomorrow. I'm not exactly sure why that's the solution. Kind of confused actually. Maybe watch another video on Quicksort or something. Thank you guys for watching. End of day 14. See you all tomorrow.